Hi, we have come to composite function. A composite function is a function of a function. Let me illustrate to you using an arrow diagram. Now you have the domain of G. Now the domain of G is x, y, and z. The members of the domain are x, y, and z. And then it's mapped onto the range of G. Alright, this is the range of G. Maybe I just write it down. This is the range of G. Now, the range of G is then mapped onto F. Okay, and so this is the range of the composite function, range of Fg. Now, in short, let's say if I can replace, you can see that there are two functions here. Let's say if I can replace these two functions by another function, all right, such that is such that for the same domain, I will get the same output. All right, let's say I find another function, all right, that can replace G and F. All right, I put it inside. All right, let's say I call this H. The function is H. All right, I put the same domain of the first function into the new function H, and then I got the same output. Now H is then called a composite function. All right, so H will be equals to f of G. Now f of G means we do G first, we put G into F. Now, how to find the domain and range of a composite function? Now, as you can see, the domain of a composite function Fg, all right, let's say we take for an example, this example, Fg, all right, then the domain of Fg is equals to the domain of the first function. All right, so this will be the domain of the first function. All right, so the domain of the composite function is a domain of the first function because this is what you put inside the composite function. We are coming to how to find the range of a composite function. There are two methods. Now, let's talk about the first method first. All right. So, all right, method one. Method one uses the rule. The rule means the composite function, the rule of the composite function, and the domain of the composite function, the rule and domain of the composite function. Okay. Now, maybe it's easier for me to show you using an example. Let's say I have a function called g of x, and that is equals to 2x. Now, what is the domain of G? Now, the domain of G is in between 0 and 2, non-inclusive. And I have another function called f of x, and that is given by x minus 1 whole thing squared. And x is a set of real numbers for f. Now we want to find the range of f of fg. All right, that is what we want to find. So according to this method, we must find the rule of fg first. So what is fg? Fg of x. That means I put g into my x. So I will have 2x minus 1 whole thing squared. Now let me just draw the graph of this graph, the graph of fg. Okay. Now, this graph will look something like this. Okay. Now it has a turning point, all right, at x equals to half. So this is 0.5. This is 0. And then maybe this is 2, all right, I call this 2, right? Because the domain of fg is the domain of g. So the domain of g is from between 0 to 2, all right, non-inclusive. So this part is the domain of g, which is equals to the domain of fg. Now what is the range of this function? All right, the range of this function will be given by this. All right, you look at this. Okay, will be here. Now, so the range of fg is given by this. So this is the range of fg. Okay. So what is the range of fg? You look at this. Now what is this point? What is the coordinate of this point? The input is 2. All right. So I put 2 inside. Then I will get 4 minus 1 and square it. So I will get 9. All right. So this is 2, 9. All right. So my range of fg will be equals to, will be from 0 to 9, non-inclusive. Wait. 0, inclusive, sorry. Inclusive of 0 and non-inclusive of 9. All right. So this is a close parenthesis. Okay. Now this point is not included, all right, but this point is included. So that's why this is inclusive of 0, but not inclusive of 9. So this is the range of fg. Now we have come to method 2. Just now we have done method 1 as to how to find the range of a composite function. We will now start with, I will now explain method 2. Now method 2 is based on the range of the first function, in this case g, all right, because we are still using the example, all right, the first function is g, all right, and the rule of the second function, that is your f, all right. Now let's look at this. Okay, now this is g of x, this is the given domain, it's the same example as just now, and this is f of x, and this is its domain. Now in this case we don't need to find the rule of fg. Now this method is good for, you know, sometimes it's very hard to find the composite function, all right. So it's, if we come to question that it's very hard to find the rule of the composite function, so normally we can use this case, all right, this method. Now let's look at this, let's sketch this graph f of x. So let me just draw the axis. Now there is a turning point at x equals to 1. So let's say I call this point 1. Okay, and then the graph will look something like this. Right, it will just go on and on. Why? Because it's a set of real, the domain is a set of real numbers. Right, so the graph will just move on and on and on and on. Now you look at it, but this is the graph of f of x. Now for the composite function, all right, first you put the domain of g, or the first function, into g, all right, then you get the range of g. Now from the range of g, you put the range of g now into f to get fg. All right, so the range of g now becomes the domain of f. That means the range of the first function becomes the domain of the second function. So what is the range of the first function? All right, the range of first function, all right, so oops, I have erased the other graph. Okay, no, this is a straight line. All right, so the range of g is what? So maybe we can just determine the range of g. The range of g, all right, this is an increasing graph. All right, the range of g will be, you put 0 inside, so you got 2 times 0, you got 0, so it's from 0 to 4, non-inclusive, because the range of g is non-inclusive. So now you are going to put the range of g into f. All right, so maybe 4 is here. Okay, so this is, what is this part? This is the range of g. Okay, now you put the range of g into f. All right, what is the output? Now you look at it. Okay, now what is this point? This is the highest point and this is the lowest point. So what is the coordinate of this point? All right, this is 4, so you put 4 inside here. So this is 4 minus 1 is 3, 3 squared is 9. So this point is 4, 9. Okay, so this should be a open full stop. The range of fg will be given by this. All right, the range is the y-axis, so this is the part. Okay, so it's inclusive of 0 but not inclusive of 9. Okay, we move on to the existence of a composite function. Now not all composite function can be, or not all function can be combined into a composite function. So when can we combine them into a composite function? Now we are going to use the same example. Now maybe I tell you the logic. No, I will tell you the logic later. I will tell you what is the rule. All right, now the rule is such that the range of the first function must be a subset, all right, or a proper subset of the domain of the second function, right? If this satisfies, then it exists. Then I say Fg exists. Okay. Now this is the rule. I didn't tell you why. Okay. The rule must come from somewhere. Let me illustrate to you the reasoning of this using the arrow diagram. Now, let's say this is the domain of G and this is the rule, all right? So every member in the domain of G has one image, all right? It is mapped into 1, 2, 3. Now, let's say the domain of F is as such, all right? This is the domain of F. Now, you will find that, all right, all these have a member. Okay. Now you look at this. X is the domain of G and is also the domain of Fg. All right. And then it mapped onto 1. But 1 is stuck over there. You cannot map onto anything else because the domain of the second function does not include 1. All right. So this X, all right, does not have any member in the end. All right. So if you put in this X into the composite function Fg, all right, it's stuck, all right, halfway, and then there's no output. Now if you look into the definition of a function, the definition of function is such that every member in the domain must have an image. Okay. Now, so in this case, there's no image for X. So the composite function Fg does not exist. Now let me just erase this. Now let's look at another scenario where this is the domain of F. All right, this is the domain of F. All right, you have some members here. Maybe you have a 4 here, you have a 5 here. Okay. Now, all these will have an image. Now, if you look at this, all right, 4 and 5 does not have any images. But 4 and 5 is not part of the domain of G. But every member in the domain of G has a input. Because if I put this into a composite function, then X will map into A, Y will map into B, Z will map into C. Right? So every member of the domain of G, which is also the domain of Fg, has an image. So for that, all right, for composite function Fg to exist, that means the range of G must be a subset of the domain of F. All right, the range of G. This pink one is the range of G. All right, must be a subset of the domain of F.